In this video, we want to compare the solution set for Chem 212 Organic Chemistry, IMSU State University, the section of 2017-2018. The number one question says, differentiate between a soft and hard base. Explain the concept of nucleophilicity as it relates to basicity. Alright, the answer to that is that a hard base is one in which the donor atom is of high electronegativity, high polarizability, and is hard to oxidize. An example of hard base is we have OH, or we have OR, and we also have this. These are examples of hard base. For a soft base, it is one in which the donor atom is of low electronegativity and is easy to oxidize. Example of soft base is, let's say, ROS minus, and even this, and SCN minus. These are soft base. Now, for nucleophilicity, it involves electron donation to carbon. Basicity involves electron pair donation to hydrogen. When a base is soft, it promotes nucleophilicity. Hence, since basicity data are always available, they can be used as a guide to nucleophilicity, provided like is being compared with like. Question 2a says, using hyperconjugation, explain why the ethyl group is more stable than the methyl group. Now, the answer is that if, for example, let's look at this compound. And then let's call this one II. Okay, sorry, made a mistake. Ought to have put in double bond. Okay, if we look at here, in the first one, there are 9 hyperconjugable hydrogen atoms, which is this 3, 3, and 3. But here we have only 5. That is why ethyl group is more stable compared to the methyl group. Number 2b says, with an example, explain 3 conditions for resonance. Now, the first condition is that the only way structures will contribute to resonance is if the relative positions of the atoms are not changed. Example, if we have this structure and this, both of them are 2 different structures. They cannot contribute to the same hybrid. The second condition is that only those structures having similar energies, that is stability, can contribute appreciably to a given hybrid. An example is if we have CH3 and then, okay, let me say, and so 2 of them, they have the same energy, so they can contribute to the same hybrid. Then the third condition is that resonance can only occur when all atoms involved lie in the same plane or lie closely in the same or close plane, that's similar, nearly in the same plane. The next question says, name the following compounds. So for the first one, we need to check. The first thing we need to count is the bridge the carbon atoms that are not joined with the bridge. Now, this is carbon atom, is not joined with the bridge. This carbon atom not joined with the bridge. This on this other side, another 2 carbon atoms. So because of that, we first of all count them. The number 2, so on this side we have 2, on this side we have 2, so we separate them with comma. 2, 2. On the bridge we have 1, so we say 1. We use parentheses 2. Having gotten that, this is one side, this is one side, so we call it bicyclo. Sorry, bicyclo. Bicyclo 2, 2, 1. Now the whole carbon atom we have 1, 2, 3, 4, 5, 6, 7, and 7 is hepta. So since all of them is single bond, we call it heptane. So the name is bicyclo 2, 2, 1 heptane. So for here we have bicyclo 2, 2, 2, 2. So first of all count the bridge. If we start from the 1 again afresh, we count the bridge 1, 2. We write it 2, 2, and then 1. 1 on the bridge here. On this other side we have 1, 2, 3. Then we have 1. We have 1. So 3, 1, 1. Bicyclo. The general carbon atom 7. Every junction is a carbon atom. So here there is no junction here. It's just the line that crossed, the bond just crossed. So for here 1, 2, 1, 2, 1. So here there's no carbon atom, it's just a junction. On here we have 1, 2, 1, 2, 1, 2. So that's 2, 2, 2. The general is 8, so it's supposed to be octane, but if you're an IMSU student, it's in the textbook for IMSU is written as heptane. So for the last one we have 1, 2, 3, 4, 1, 2, 1, 2, so 4, 2, 2, bicyclo decane. All of them is 10, so bicyclo decane. The next question says write the formula and structures of the following: propane, cyclopropane, butane, cyclobutane, cyclopentane. So the first one is propane. Propane has the formula of C3H8. If we are to draw it, this is propane. The next one says cyclopropane. This is cyclopropane. It has the formula of C3H6. The structure for cyclopropane is this way. Now this every junction CH2, CH2, CH2. The next one is butane. Butane just has the formula C4H10. So for us to draw it, 4. So butane. Now the next one is cyclobutane. So for cyclobutane, at every junction there is CH2, CH2. That's why it has the general formula of C4H8. The last one is cyclopentane. Cyclopentane is C5H10 and the structure is this way. So at every C there's H2O. Sorry, there is CH2. CH2 at every junction. CH2 every junction. CH2. The next question says, what is the general formula of alkanes? Cycloalkanes. Define cycloalkanes. Now, the general formula of alkanes is CnH2n plus 2, where n is the number of carbon atom. So if n is 1, it means there's only one C. 2 times 1, 2, plus 1, so plus 2, that's 4. So it means one C will have 4H. So for the second one, the general formula of cycloalkanes is CnH2n. N is the number of carbon atoms. The third one said define cycloalkanes. Cycloalkanes are alkanes with carbon atoms arranged in a ring form or structure. They do not contain double bonds and they are saturated. The 4B question says draw the structure of the following cycloalkanes: 1 bromo, 3 chloro, 4 methyl cyclohexane, and the rest. So let's tackle them one after the other. For the first one, we need to first of all draw the parent chain, which is cyclohexane. So which is cyclohexane. So when we draw it, it says 1 bromo. So we come to pick 1, put bromo there. It says 3 chloro. 1, 2, 3. At the third position, we put chloro. 4 methyl. We come at the 4, put methyl. Cyclohexane. So that's just it. The second one says methyl cyclohexane. So what we need to do is first of all draw the cyclohexane. They did not give us the position where the methyl is, so we can just put it anywhere we like. Anywhere we like, we can attach it since they did not specify the position. The third one is ethyl cyclopentane. So we need to first of all draw the parent, which is the cyclopentane. Now ethyl means we put ethyl. That's it, ethyl. We draw the parent chain, we put ethyl to it. The next question says define the following: Bayer's string theory, attrop isomerism, biphenyls, allenes. So let's pick the first one, Bayer's string theory. This theory states that the stability of a carboxylic compound depends on the amount by which the angles between chemical bonds deviated from the value of the angles subtended by the corners and center of a regular tetrahedron, which is 109 degrees 28 minutes, which lies between the values observed in the regular pentagon 108 degrees and regular heptagon 120 degrees. Attrop isomerism is the type of isomerism that arises from restricted rotation about a single bond and where the stereoisomers can be isolated. The next one is biphenyls. Biphenyls are polynuclear hydrocarbons with 2 phenyl groups attached together with a single bond. I think I need to show this one. This one on the para position. So they are so here is para position. Here is para position. So here So here is the auto position, here is the meta position, here is the meta position, here is the auto position. So this is a biphenyl. The last one is allenes. These are compounds whose molecules contain cumulated double bond sequence. Example of allenes, let me use this. CH2 double bond, CH2, and then so this is an example of allenes. Allenes with different substituents on end carbon atoms are said to be chiral. The next question is, what is structural isomerism? Now, let's answer that. First of all, isomers are molecules that have the same molecular formula but have a different arrangement of the atoms in space. So, structural isomerism, or it is also called constitutional isomerism, they are compounds that have the same molecular formula but different structural formula. That is in the order in which the different atoms are linked in the molecules. For example, butane has two isomers. So butane has two isomers. This, the normal butane, and this. Pentane has three isomers. So this structure is different from this structure, but the same number of hydrogen, the same number of carbon, the same, but the two are different. So this is butane, this is 2-methylpropane. The next question says, list the 5 types of structural isomerism and explain any 3 of your choice. Now, let's begin with the chain or nuclear isomerism. Now, in this type of isomerism, it is shown by compounds that differ in the arrangement of carbon atoms only. For example, if we have the normal pentane, CH3, CH2, CH2, CH3, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, sorry, CH2, CH3, 1, 2, 3, 4, 5. So this is the normal pentane, and its isomer is isobutane. You can have CH3, CH2, CH2, and CH. Okay, CH alone and CH3. Then here we can have a methyl group, isobutane, 1, 2, 3, 4. So this is isobutane and this is the normal pentane. So the only difference is just the shift in carbon atoms only. The next one is the position isomerism. The position isomerism, it is shown by compounds having the same carbon skeleton but differ in the position of the substituent group. An example is if we have 1 bromo, 1, 2, 3, 4, and then we have a bromine atom. This is 1 bromo. The first atom, carbon atom, is where the bromine is, 1 bromobutane. And then we have 2 bromobutane, which is CH3, CH2, and then we have the bromine attached at the second carbon atom. So we now have CH2 and CH3. So it's just the substituent is what is changing the position. Bromine is just what is changing. So we call it positional isomerism or position isomerism. The next one is functional group. Isomerism. It is shown by compounds having different functional groups. That is, they belong to different homologous series. Same molecule, but formula is different. Formula is different functional group. Example is if we have CH3, CH2OH. This is ethanol. Now, and we have CH3O, CH3. Now, this is a methoxymethane. So you can see different functional group. You can also have another example like acetone and propione aldehyde. Two of them. Let me write it. Acetone is CH3C double bond O CH3, while propionaldehyde is CH3 CH2 CHO. So you can see two of them, different functional group. Another one is metamerism. This is a type due to unequal distribution of carbon atom on either side of the functional group. Now, the members belong to the same homologous series. Example is if we have dimethyl ether. Dimethyl ether, methyl on either side, dimethyl ether, and then we have methyl propyl ether. We can have methyl propyl ether, methyl propyl ether. So two of them, metamerism. We also have tautomerism. We have tautomerism. This is a special type of isomerism. Is a special type of functional isomerism in which the isomers are in dynamic equilibrium with each other. An example is if we have this cyclohexanone. Let me write it. Cyclohexanone in equilibrium with, and this is one cyclohexenol, because of the double bond hexenol. 4b says define mesocompounds. Now, a mesocompound is a molecule that contains a chiral center. But is achiral as a result of having a plane of symmetry in the molecule. What we mean by that is, for example, if we have this Cl, we have OH, and here we have H, and here we have Cl. So if it is rotated, we'll have Cl coming over here, OH coming over here, and H coming over here, then OH coming over here, then H coming over here, then Cl coming over here. So this is internal plane on here. So moving further, we have OH, Cl, and then we have Cl, we have H, OH coming here. It can form a mirror image of, this is different, it can form a mirror image. Here is mirror image. The mirror image is, we can have OH here, still have H here, Cl here, then we have Cl here, we have H here, we have OH here. So this is the internal plane. So this is one trans 1,2-dichloro 1,2-ethane ethanediol. Let me write it. Trans 1,2-dichloro. So dichloro, 1,2 ethan diol, ethane diol. The next question says, write on 3 properties of enantiomers. Number 1 property is that they are stable, isolable compounds that differ from one another in 3-dimensional spatial arrangements. The second property is that they cannot be interconverted under ordinary conditions. So what we mean by that is that you require extraordinary conditions, a special condition for you to interconvert them. The third property is that they have the same melting points, density, solubility, color, and reactivity towards acids and bases. The next question on 5a says we should explain how inductive effects affect the stability of acidity or basicity of a chemical species. Now, electronegative atoms draw electrons towards themselves. We need to understand that, which can stabilize a conjugate base. Groups that have inductive effect on a molecule decrease its electron density, making the molecule electron deficient and more acidic. Example, the conjugate base of benzoic acid is stabilized by withdrawing groups. So that's what we call electron withdrawing groups. This makes the acid more acidic by delocalizing the charge of carboxylate ion. So the second question there says we should explain why it is not profitable for aniline to take up a proton. The answer is that when aniline is protonated, no delocalization and stabilization is possible because the lone pair of electrons are lost. What we mean by that is, okay, let's draw. If this is aniline, so we have the lone pair of electron. So the aniline is a neutral molecule, so it is stabilized with respect to anilum cation. So the next question says, number 6, leaving groups affect nucleophilic substitutions. Let me write. So leaving group affects nucleophilic substitution. Using the halogen, explain this observation. Now the answer is that changing the leaving group will alter the rate of both the nucleophilic substitution, what we call SN1 and SN2 reactions. This is because breaking of the bond to the leaving group is involved in the rate determining step. So the SN1 and SN2 follows the order Ri is greater than RBr is also greater than RCl is greater than R fluorine. So high polarizability of iodine ion makes it both a good entering and a good leaving group. The stronger and harder as a base leaving group is, the less readily can it be displaced. So that's why it is more more readily displaced as a leaving group. So leave your questions and comments in the comment section. Remember to subscribe to my channel by clicking the subscribe button if you haven't done so. Thank you.